So continue our conversation about some of the basics of electrochemistry. We're going to examine half reactions a little more closely. There was one example earlier in the last video that I pointed out some of the rules that you have to follow and so forth. But this one kind of puts it on the table pretty specifically. So to assist in various tasks related to redox reactions, it's easier to separate them into half reactions. And so in a reduction half reaction, you are going to see electrons on the reactant side because reduction is the gain of electrons. So electrons will be going into the reactant in order to make the product. In an oxidation half reaction, you're going to see electrons showing up on the product side because the loss of electrons means you have what's left over plus some electrons that are going off somewhere to do something else. The other thing that you have to do is make sure that you balance mass. Mass has to be balanced first, and also charge. And remember, the charge doesn't have to be zero. It just has to be the same on both sides. So we've got some examples on the next slide. So how do I write the appropriate half reaction for copper going to copper 2+? Well, I don't have to worry about atoms. That's pretty easy. There's one of each. But now I've got to deal with the charge. So copper is losing electrons. So this is oxidation. I'm going to put the electrons on the product side. And how many of them? Well, 0 to 2+ means I better be losing 2. So this is the oxidation half reaction for copper going to copper 2+. Next one, lead 4+ going to lead. Once again, it's pretty straightforward. The lead ions balance because there's one of each. +4 goes to 0. So now I have to actually gain electrons in order to make my neutral. So here's reduction occurring. And so I'm going to show those 4 electrons that I have to gain on the product side or on the reactant side. So notice in both of these cases, total charge on both sides are 0. 0 here, +2 - 2 is 0, +4 - 4 is 0, 0. It's not always going to have to be that way, but oftentimes you're going to see it that way. All right, so next one, I've got chlorine going to chloride. So first thing I got to do is balance, right? So I got 2 chlorines here. I need 2 Cl- here, which means each Cl is going to be losing 1 electron for a total of 2 electrons, not losing, gaining. So this is neutral. This is -1. So I'm going to have to gain a total of 2 electrons, each chlorine gaining 1 in order to get the balanced equation. So now here's an example where you have charge balancing out at -2 instead of balancing out at 0. But I have same number of atoms on both sides, and I have total charge, the same on both sides. And since I'm adding electrons, this is reduction. Next example, and we're keeping this very simple. You're going to see reactions start to get really complicated with redox stuff. You're probably wondering, why do I have to worry about oxidation numbers? This is pretty easy. Well, yeah, I'm keeping it easy for right now. All right, so N3- going to N2. Each nitrogen, or each nitride, is going to have to lose 3. I need a total of 2 nitrogen atoms to make N2, so that means 2 of these guys are going to each have to lose 3 electrons. So I'm going to have to lose a total of 6 electrons. So that's oxidation, 6 electrons being lost, 2 N3- going to N0, and therefore oxidation. I think that's all the reactions I have. All right, so now what if you're given a situation where you have the 2 half reactions and you have to add them together? So you didn't start with the overall reaction, you started with the 2 half reactions. So how do you get to the final overall reaction? So to add the 2 half reactions together, you need to make sure that both atoms and charge balance and the electrons have to cancel out. So let's say we want to add the half reactions between copper and lead together. Okay, so copper going to copper 2 plus 2 electrons, lead 4 going to lead neutral. So to add these together, I've got to make sure my atoms are going to balance. Okay, well, 1 to 1, 1 to 1, that's easy. And now I want to make sure that the charge is going to balance. So the electrons have to cancel. So I can't have this guy losing 2 and this guy gaining 4. Where do those other 2 electrons come from? So I'm going to have to multiply this whole reaction by a factor of 2 in order to get it to the point where my electrons will cancel. Okay, so kind of like we did with Hess's law and a few other ways you saw, when we add them together, we're just going to combine all the stuff on the reactant side, all the stuff on the product side. But notice we've got 4 electrons and 2 times 4 electrons, so they actually wind up canceling out. So this is kind of the overall reaction that you're going to get. Remember, I had to multiply the copper by 2, so I have 2 coefficients for the 2 coppers, and nothing really happened to lead. So if I do another example, here's my 2 half reactions that I want to add together. I've got 2 electrons here. I've got 6 electrons here. Well, that's not going to work. So first thing I want to be able to do is make sure that my electrons are going to cancel out. So I'm going to multiply this whole equation by 3, which means overall I got 6 electrons to cancel out, so I don't have to include those. 3 chlorines, 6 chlorides, 2 nitrides, 1 N2. So you see a couple of examples and it makes sense. Sometimes it gets a little hairy when you try and do it yourself. So be patient. Sometimes they don't work out very easily. So you got to be patient. Okay, so when you balance redox reactions, you got to remember a couple things. Just as review here, you have to obey the laws of conservation of matter, so you need to make sure your atoms balance. We also need to balance charge, and we're going to do that as a function of the electrons. You have to have just as many electrons being gained by something as you have being lost by something. Simple redox reactions are going to balance the charge pretty much at the same time that you balance the mass. As they get more complicated, not so much. It's going to require a little bit more work to balance the complicated stuff, and we're going to look at the more difficult balancing of redox reactions on another day, in another video, actually probably in a long time of long discussion in class. All right, the one other thing that I want to talk about is the idea of an activity series. Activity series are really showing you kind of the order at which certain things undergo oxidation, or how easily certain things undergo oxidation or reduction. So it's really showing you the activity of the loss of electrons or the activity of the gain electrons. If something loses electrons easily, it's going to be very active, so it's going to be high up on the list. If something loses electrons more slowly, it's going to be low on the list. Elements can be arranged in either order, increasing oxidation or reduction. Oh, I guess low activities at the top, more activities at the bottom. Sorry, said it the wrong way. And an activity series is actually going to be used to predict the outcome of a reaction between materials. So we'll get into activity series right now because here you've got an example. So typically the materials at the top are more likely to undergo that reaction. Okay, I was right the first time. So increasing activity at the top, decreasing activity on the bottom. So lithium really wants to get rid of that electron. It's at the top of the oxidation reduction, or the oxidation activity series. Gold, on the other hand, doesn't want to lose electrons. So things at the top would prefer to be the product. Things at the bottom like it the way they are. They want to stay this reactant. So this gold does not want to lose electrons, but this lithium is pretty much giving them away. So what you're going to do is you're just going to use the location to predict, use the 2 locations to predict which one's going to go more easily. So now it's not everything at the top oxidizes fast. Everything at the bottom oxidizes slow. It's a matter of ranking. Where are they? So lithium is going to lose its electrons more readily than potassium will. Also, when you take a look at an activity series, you have to have the combination of elements. Something's going to go undergo oxidation. The other thing is going to have to undergo reduction. So you've got to think about it as the reverse. So you're going to see something along one of the species you're going to be given will be a reactant species. The other thing you'll be given is the product species. So let's I think it's easiest to just do some reactions here. So Mn and Cu2+. So let's find them on the activity series. Here's Mn, and then Cu2+ is down here. So Mn is higher up on the activity series, which says Mn would like to be Mn2+. Cu2+ is further down on the activity series. What that tells you is Cu would rather be the reactant. So these guys would rather be the product. These guys would rather be the reactant. So at this point, they are not. They're the opposite. So this reaction will occur because manganese is higher on the activity series than copper 2+ is. Oops. I was thinking the answers were going to pop up, so I guess we got to do all these together. So lithium and iron, Li+ is up here. Lithium is the one that most wants to be Li+. So it doesn't matter where iron falls. Lithium's up here and it's an ion. It is going nowhere. So this reaction is not going to happen. Iron winds up being way down here. It's further down on the chart than lithium is, so iron would prefer to be, compared to lithium, iron wants to be the solid. Sodium and calcium, ion, sodium's here, calcium is just above it. So calcium is in its preferred state. Compared to sodium, or compared to calcium, sodium is also in its preferred state. So this reaction's not going to happen. Aluminum 3+ and mercury. So aluminum is right here. Mercury is way down here. And they are in their preferred states already. Aluminum's at the top and it's an ion. It's not going to change. Barium and lead 2+. We've got barium way up here. We've got lead way down here. Barium's the one that wants to be the ion. It is not the ion, so you're going to have a reaction. Barium and lead 2+ are going to react to give you the opposite guy. So you're going to get barium 2+ and lead metal. And so that kind of gives you an idea of activity series. If we didn't have all those, never mind. If you take a look at when you put things in, mix things together, we've done a few of these at various times. Zinc and zinc metal and copper ion are in their unpreferred states. So you are going to see a reaction happen because zinc wants to become the ion and copper wants to become the metal. So copper ion is going to accept the electrons that zinc gives up, become the metal, and form the solid on the surface of the metal. The zinc is going to become ions. So that's how you can use an activity series, or you can develop your own activity series. And you can rank them in order in terms of how often do they react. Something that reacts more means that it would rather be, some solid that reacts more means it would rather be the ion than the metal. And now we're done because the next conversation is balancing harder redox reactions. So we're going to quit here and talk about balancing in the next video.